everybody in here. All right. So I wanted to start off just seeing if you guys had any questions. Chapter 7, we're at this weird spot in the course where for a few days it's chill. And then, yeah, this is like the only time we can actually talk to each other and ask questions a lot. We've got lab tomorrow all day for questions, which is going to be awesome. But I just thought I'd check with you first before I start babbling about something. Is there anybody that has a specific question about anything in chapter 6 or circular motion, friction or forces? Anything chapter 6? I
actually have a question.
Yeah, go for it.
I needed help on finding, I think it's for 6.63. I'm pretty good on like doing the FPDs, but I'm kind of struggling on finding, I think it was Vmax on that one. I'm just
okay. So let me share screen. So we're going to look at 6.63, everybody. If you could get that up. 6.63. Is that one of those bank curve ones? Yeah, this is on page 117 if you need it. Okay. So let me just do this really quick. That way, if somebody's watching the live stream, they've got it. Hold on. Let me speaker view me. Okay, 6.63. I'm going to pause for a second. Wait, wrong page. Oops, sorry. I'm zooming it up. 6.63. Sorry, I don't have that file open right now. So there it is, 6.63. All right. So hopefully you've got it in front of you there. Carter, and so maximum speed. All right. So in this case, when the problem says maximum speed, that's supposed to give you a hint about something you can use in the problem. Specifically, when it says maximum speed, right, it's going around something. This tells us a couple of things, right? And I think you said you got the FBD right. So I'm just going to put that up here really quick. So this is the car. Let me get some different markers here. All right. And so in this case, I'm drawing a rear view. There's mg. There's the normal force. If you're going too fast, which way do you tend to slide? Towards the inside or the outside?
The outside.
So which way does friction point?
It's going left, down the plane.
Down the plane. Yep. Good. I like that. Okay. These arrows aren't to scale. And then which way is this thing accelerating?
Would it be to the left?
This way?
Yeah, towards the center.
Yeah, I agree. Okay. And it's straight left. So there's a C, and it was moving it. We're assuming it's at some constant speed. And then the extra piece, Olivia's having some trouble trying to get in here. Whoops. Hopefully that worked. All right. We'll see if she's able to get in. In this case, what does this tell us if it says max speed? What does that tell us about the friction equation? Which one applies?
Is it mu static?
That's right. So friction is mu static times the normal, and it's okay to use the equals for this one. Okay. And so, all right, so far, that's all good, you said, right?
Right.
Okay, so let me just get up here. Oh, I've got this one. Hold on, zooms. Got a lot of stuff open here. Let me hit Control F. I think you said it was 6.63. That one. Okay. Oh, I see. So just doing the algebra. So it says I use style 2. See the previous problem. So let's go back to the I guess it was a couple problems ago. I used this style right here. Do you agree this one looks about the same?
Yes.
And so in this case, I used basically these equations. All right. And so let me just write that up here. So we're doing style 2. We've got the FBD up there. I believe everything in that FBD still applies exactly as is, right? Friction's down the plane. The only trick is now we can use that F equals mu n in here. So let me write these down. We get an n sine theta plus F cosine. Give me just a sec. And then down here, we get an n cos minus F sine equals mg. Okay, and then just give me a second. Man, I feel sorry. Olivia's having trouble. If anybody knows how to contact Olivia's here, I don't know. I'm trying to let her in here, but all right. She seems to have a lot of trouble today. Olivia, did you make it in? Yay, all right. I don't know what was happening there, Olivia. All right, I'm glad you made it in here. Okay, so now at this point, what I would do, Jose, was, I think this was your question, right, Jose?
Right.
I'm going to just do this trick. If it's on the verge of slipping because we're at max speed, I can replace these with mu static n. So far, so good?
Okay.
Now, what do you think I might do next? It's just take a guess. It's okay to be wrong.
You maybe take a ratio?
Yeah, sweet, dude. All right, so what's going to drop out on this side when you take the ratio?
Would it be the ends?
The ends, absolutely. Just getting another color here. Whoa, crap, wrong one. The end drops out. Mu static is still there. Let me clean that up. So if I divide every term by n in the top and bottom, right? The ends drop out. What drops out on the other side?
M's.
M's. So far, is this okay?
Yes.
All right. And then what are we supposed to solve for? I forgot already.
For V, but AC is V squared over R.
Yeah. So, all right. So we're almost there. Do you agree? So on this side, you get sine theta plus mu static cos. And on the bottom, I think we get cos minus mu static sine, right? And
Right.
then on the right side, we get V squared over RG. Do you believe that?
Yes.
So then do you agree I could cross multiply and take the square root?
Uh-huh.
Now, I should check the units before I get along too far here. When I take the square root, that gets rid of the squared. This RG, I don't know if you remember, we've seen this a lot. This is actually the right units. It's meters times meters per second squared, and then you're going to square root. So that's going to work out. So far, so good there?
Yes.
And then how could I get tangent involved? Do you remember? What do I do to each term in this fraction to get tangent to appear?
The times like 1 over cosine?
Yeah. Now I'm writing it kind of small because I screwed up there. But if I divide all those by cosine, what are we left with?
Yeah, that's tangent.
Yeah, tangents and some stuff, right? So I get an RG. I don't remember if I used uppercase. Whoops, sorry. Give me just a second. Oh, sorry about that. I accidentally pulled my headphone cable out, and when I do that, Zoom locks up on me. Sorry about that. Zoom locks up on me when I accidentally pull my headphone cable out sometimes. So it probably froze. But so I just waited. Sorry about that. So V is RG like this. Jose, are we still good with this equation?
Yeah, that makes sense. I think the issue I had was I left friction in front of cosine and sine without putting in the mu static n, and that's probably why my ratio, because I was doing ratios, but I had one n left over, and I was, racking my brain on why I still had an n there.
And this, you'll see this a lot, where if you don't remember that step of plugging in that one word, maximum speed, the max speed is what says, I can use that. And if you forget that, it's impossible.
Right.
Just like you encountered.
Yeah.
So that's why reading that question carefully, and I'll probably put this on the quiz on Monday, where I literally ask you to think carefully. Do you use mu kinetic times the normal force, mu static times the normal force, less than, or is it inconclusive? Now, in this particular case, it was conclusive. Use mu static times the normal force, and that's what got us going. Is that? And let's make sure that was the actual answer in the book to make sure there was no typo. It was the next question. So I had mu plus 10 and 1 minus mu 10. Yeah, it's the same thing. I switched the order, but there we go. So that's it. Cool.
Yeah, that was good.
And
thank you.
Those kinds of problems, you could see, like, another way I might do this is just do the same exact problem, but ask you to solve for the radius. And then what happens is the procedure, the physics is the same. And what happens is maybe one or two of the algebra steps get flipped. But so this is probably one of the trickier ones because, yeah, I don't know. You could have done it. So Jose, another thought you could do, just kind of, I'm trying to give you ideas for things you could do if you get stuck on test day, right? So if you go back to this one, you could also try right here. Solve that for F. And then you're pretty used to in the early part of chapter 6 saying, okay, well, I'm just going to take this and multiply by mu. Well, you could solve this for n and multiply that by mu and shove it in, and you would get the same result as well. So you could use either of these two styles here. Let me just get it both up there. They both give the same answer. And you could argue, well, I understand style 1 better. If you understand style 1 better, by all means, use style 1. Does that address that one, Jose, as well? Just kind of a different way of looking at it? What do you think?
It definitely makes sense. Like I said, that
Oh, I lost you. All right, I'm going to assume he got that. Sorry, Jose.
Was I not talking?
Yeah, it muted out. Sorry.
Yeah, no, I'm saying it was just not plugging in that friction will really screw me over.
Yep. So you got to look carefully in the words. Can you use that or not? All right. Okay, cool.
Could we go a little bit more into detail about the conceptualizing the whole friction thing? So my question is,
okay.
Is that okay?
Yeah. I just don't understand. So yeah.
Yeah, sure. So you're saying, so what I'm trying to understand is, so when it's ideal speed, you're on the plane and there's no friction, right? And so when you say max speed, we're not. I see when I thought max speed, I thought, okay, the car is moving up the plane. But it's not high. It's kind of like saying the max speed before it starts moving up the plane.
Correct. And that's what's ambiguous about this wording. Like, you'll often hear, what's the value that causes this to slip? And then when you hear that word, you're like, oh, it's slipping. But in reality, when you do the math, what you do is you say, okay, first I'm going to find the largest value that works without slipping so that I know any slightly larger value would slip. And so that it's finding that critical point. And generally speaking, what we do is we find that critical point by saying it doesn't slip in all of these, even though the problems often sound like it's slipping. And now let me see if I can find, let me see if I got this. Hold on a second. Wait, whoops, lost it. Let me do, let me see if I got this simulation here that might help.
And so if it was greater than max speed, you would just end up going off the plane. Is that what would happen?
Yeah, let me share screen to try and give you a visual for this. I used to have an animation that would actually show the car driving around, but this is the best I could find right now. So it's a Java, and they got rid of Java like at the beginning of this month. So I'm like, I don't have time to find another one. But so this is the simulation that we have right now. Let's say you have a very small coefficient of friction here. All right. And let's say our radius is pretty big. And let's make our angle pretty steep here. So 13 like this. Let's go like this. So this might actually be, this is kind of absurd. You don't see a lot of roadways banked at 20 degrees, but let's say it is, right? This might be an on-ramp or something, and an extremely strange on-ramp. The idea here is, I'm looking at this slider in the middle of the screen. Give me a second so I can circle it. I'm looking at this slider right here. So the idea is this is showing you all the speeds where you can go around the turn safely. And so if I drive anything up to about 24 or anything down to about 14, there's enough friction to keep me from sliding to the inside or outside. But if I go into the danger zone, I'm going to slide to the outside because I'm going too fast up here. So if I was driving faster than this 23.8 meters per second for this set of conditions, this angle, this mu, this radius, the maximum speed I can go without sliding to the outside and wrecking my car is 23.8 or so. The smallest I could figure out is about 13.4. So again, if you go slower than 13.4, you're going to slide to the inside and you will not be able to navigate the turn. So what we see then in general is, depending on the coefficients of friction and the radius and the angles, there's a range of safe speeds. So what a civil engineer is going to do is try to pick a range of safe speeds that people normally drive in that area and make sure the road is safe, even if the coefficient of friction is low. Now notice if we go lower and lower, the range of safe speeds gets smaller and smaller. So when the roads are icy, there's a lower probability that person will be driving at the ideal speed. And so if there was really no friction, there's only one ideal speed here. Oh my gosh, it's tough to get there, but it's about 19. Okay, so let me just bump this up to just 0.1 or something. Sorry. Oh my gosh. All right, 0.02. The idea here is, notice in the FBD that's shown in the middle, look at this FBD in the middle. Right now, there's no frictional force. This means we don't need any frictional force to keep this thing in the banked curve, right? We're right at the ideal speed. And then what happens here is, if you change the coefficient of friction higher, you still don't need any friction. You're still at the ideal speed. However, this would be on the verge of slipping out. This would be on the verge of slipping in. That helps you determine your range of safe speeds. And then anywhere in between here, like look at this. Let's look at this one first. Okay, we're about to slip to the outside. Make an observation right now of the amount of frictional force. Okay. And so the idea here is, if I go to a slightly lower speed, notice that frictional force, I don't need all of the frictional force. All right. And so this is why we sometimes call F equals mu static. That's not the friction that's applying in this case. That is the maximum possible amount of friction that this roadway could exert on the car. For this particular example, friction is actually less than mu static times the normal force. Esteban, is that helping?
Yeah, that's helping a lot. So how would you calculate the least amount of velocity? Because you know that mu static or friction is going to be less than mu static. You just simply do the FBD and just solve for F? Is that?
Well, so what you do is you say, okay, if you want the least, it's not exactly the same. So this would give you the most, right?
Yeah.
You set F equal to mu static N and crank out the problem and solve for V. That would give you the max speed, right? What would you do to get the minimum speed? What's different at the minimum speed?
Well, we know that friction turns around.
Yes, you point friction the other way in the FBD and do the same exact problem.
Oh, okay, that makes
Got
sense.
it? And so there is a subtle difference there, right?
Yeah, okay.
Yeah. And so, yeah, that's the trick. And so now imagine how easy it is to give different variations of this problem for a quiz. You give one person that's less than the ideal speed, but not just about to slip. Another person less than the ideal speed, about to slip. Another person above the ideal speed, not on the verge of slipping, etc. And so you could just keep going, and then you could random number generate these, and yeah. But this gives you ideas. Notice as you go flat, right? No, look at this case right here. This is kind of interesting. So what I'm looking at, let me show you what I'm looking at. Give me a second. This end of the plot. As the angle gets lower and lower, there's no risk of sliding to the inside of the turn. And so this is our usual experience in life. Most roadways are not angled above 20 degrees where you're going to slide to the inside of the turn. But like an Indy racetrack or a, you know, some very big racetrack with huge turns with cars going 200 miles an hour, right? 200 miles an hour is about 100 meters per second. You're going to need a crazy bank. All right. But so there's not always a minimum speed required. That's why we don't usually see signs on our roadways for you must drive at least 10 miles per hour. We don't see that, right? But our roadways aren't usually banked this high. So this would actually be a roadway where you'd have to drive about 10 miles an hour or faster to make it, because remember, it's times about 2.2. All right. Cool. What do you think? Questions on that? Other questions? That was a good one. The banked curve gets you kind of used to kind of realistic problems, right? Any real civil engineer probably has, there's already a cookbook for this, but the process of having to learn this shows you you're gonna have to make your own cookbooks as an engineer, set up your own spreadsheets and simulations like this. So it kind of sets the stage for it. Awesome. Other questions?
I have another one.
Yeah, go for it.
So I just had a question on 6.62 because I did style 2. How would you find was like normal force for style 2?
Let me see.
Because I know
So
if you use style 1, I mean it's pretty self-explanatory, but then doing it for the other one, you know, it gets,
yeah, that's pretty challenging, isn't it?
yeah.
What you could do is you could plug in mu static n right there. So if you plugged in mu static times the normal force for that one, then factor out the n's, so you get n times sine theta plus mu cos. Do you see that on the left side?
Right.
And then you could divide this all by that, and you could get it.
Okay.
And so now, remind me, in 6.62, I just want to check. Let me read that. I'm reading 6.62. The figure is similar, typically friction. Okay. Wait a minute. This is not legal for 6.62. This wouldn't be legal. This would be legal for 6.63. This was valid for 6.63, but in 6.62, they didn't really tell us that friction was equal to mu times the normal force. So it would be even worse than this. What you could do is solve this equation for F. Then take that equation and plug it into this value of F, and look how ugly it gets. But it would work, right? And now keep in mind, once you do that, so I've got this up on the screen, up on my whiteboard. Hold on. So the question was, in 6.62, how would we do this? In 6.62, how could I use style 2? And here we see it's much harder to use style 2, but this was not valid. So let me just get us caught back up. This is a good question here. Sorry. Probably would have been faster just to erase and rewrite, but okay. So I believe this was an N, this was an F, this was an F, this was an M, this was an M. All right. So the question was in 6.62, nothing indicated that it was on the verge of slipping. Do you agree, Jose?
Yes.
And so in 6.62, just to show you the wording for that in case you don't have it right in front of you, I've got it right here. 6.62, you could pause and read it later, but nothing in that wording says it's on the verge of slipping. We don't see any min or max or about to slip or anything. So what you could do in 6.62, you can't use F equals mu static N, not allowed. So what you do is you could solve this equation for F. Now this is always dangerous trying to do it in my head, but I think F sine theta is equal to N cos theta minus mg. Move that to there, move this to here. Then divide this by sine theta. Now you could take this result right here stick it in right there. Whew. And notice there's an N here and an N there. Then you could group the ends and solve for it. What we see is that's tough compared to using style 1. And so this is what I realized a few years back. So notice style 1 is just move this to the other side of the equation, plug in the numbers, and you're done. It's so much easier. And so I used to tell people to use whatever style they want. And then a few years ago, I switched to, you should just learn both, just because I have no idea what I'm going to put on the test day. And I don't even think about this, right? Because I'm like, I choose the coordinate system to match what I'm doing. And I was, yeah. So some students would have it much easier on the test day if they happen to really like style 1 for a certain type of problem. And then a different year, somebody might have a much better time if they liked style 2. And so, I don't know, Jose, is that helping you?
Yeah. So then, at least for a question like this, would you say then maybe doing 2 FBDs of either style would be helpful?
What I would do is draw the FBD, but don't write the coordinate or the equations. Then read the problem carefully and say, what's trying to be solved? So, because then you don't waste a lot of time. You could do exactly what you said, but that might waste time. So what I would do is I would draw the arrows and then I would read the question. And it says, and you can even write this down on a piece of note paper because we're doing class online. You could just scribble this right in your workbook, right? If you're like bank curves, right? Your notes are fair game on your test. So you could come in here and say, look, I know if I'm doing F, N, or mu, those appear here. Here, I'm going to line up the coordinates to match F or N because it's less work. And then if I'm looking for VA or R, or I guess if you wanted to get the mass, well, that's tricky because mass always drops out. But yeah, but so if you're doing VA or radius, you might want to do this other one over here. If you were trying to find the angle, boy, I'd have to go to a computer code probably just because that's practical. Jose, does that help?
Yeah, that makes sense. Thank you.
Yeah. Cool. Other questions? This is good stuff. Good stuff. How about the beginning of chapter 6? Are people feeling, I'm just going to go to the gallery view here. Are people okay with the beginning of chapter 6? Meaning like blocks on planes and friction, or 2 blocks with a string and a pulley. I'm hoping you're kind of better at that than the circular motion. That's why I've spent more of my time on circular. But any questions about that stuff? Okay. And if I'm not giving you enough time to respond, just interrupt me. Okay. But I think just in the interest of time, I'm going to go on to chapter 7. My reasoning is the sooner we get through chapter 7, which is a very short chapter, the more time we could save on chapter 8. And if we have a little bit of extra time for chapter 8, we might be able to use the last half of the day right before spring break, which is coming up in 2 weeks, thank goodness. We could maybe use that day to catch up on chapter 8 as well, or start chapter 9 or whatever you want. So I'm going to go ahead and push into chapter 7. Remember, show up to lab the first 15 minutes tomorrow. We'll talk about the schedule and where things are located and what changes I've made, because we haven't addressed that. Oh, there's a question in the chat maybe. Okay, all good. Thanks. Yeah, so we will and then tomorrow, if you have time, do a practice test before you show up. Take it for 2 hours and give yourself 2 hours. Don't look at the solutions. Don't freak out if you fail it. And then what you could do is you could take another one during the lab, and you could ask me any questions you have, and you've got the solutions to grade it. Now, if you don't have time for that, I understand. If you want to do the practice test over the weekend instead, that's fine. If you want to do chapter 6 problems all day tomorrow in lab, in Zoom with me helping out, great. If you want to do them on your own and pop in and out, that's fine after that first 15 minutes, okay? So at least show up for the first 15 minutes so we can make sure everybody sees all the changes in the schedule. And then after that, it's work on what you want. Practice test, chapter 6, whatever. And then our goal is to be totally caught up with chapter 6 by the end of this weekend so that we're hitting chapter 7 and 8 strong. Eight's a tough one. But, well, it's fun. It's fun. There's fewer vectors too. All right, let's go to chapter 7 now. So if you've got workbook volume 2, we're finally there. Dun, dun, dun. All right. So let's go ahead and start out. I'm ready to get to work. All right. So we're talking about this page, which is what? Oh my gosh, I'm so used to the purple book. I just grabbed it again. All right, so we are on page 3, I think, right? Yeah, 3. All right. And so work is a technical term in physics. So we're used to saying like, oh, could you work on this for me? Or gosh, do some work. Or I got to go to work. Well, for us in physics, work technically is this this definition here, right? So you've got this on your screen. I'm going to just talk about it on the whiteboard a little bit. All right. So I'm just going to give you a little bit of conceptual feeling for this. And it might, some of you may have seen this in a calculus class. I know they like to give a worked example problem on work where you raise the water out of the cylindrical tank, calculate the work done. That problem always makes me laugh because it's so easy if you're a physicist. You just say, well, calculate the center of mass and move it up and you're done. But whatever. Work, by definition, now you're going to see me try to be consistent with this. So I want to be clear here. W is weight. Capital W, and I'm going to try and indicate my capitals like this, okay, with the serif on it. And then omega is curly. This is omega, angular frequency. We've alluded to this in the last chapter a little bit. So we have to be a little bit careful just with your lettering. So I recommend that you do something in your own work to clearly distinguish between lowercase and uppercase W, just because this is kind of somewhat standard, all right? Lots of people use lowercase w for weight, capital W for work. All right, and omega is curly. Don't say W, but you know, that's fine if you do a few times. I'll try to keep correcting you. This is omega. So that's the symbols that we're going to use. Okay, work by definition is equal to the integral of a force times displacement. So ds here could mean, let's say you're going along some path, all right? This is one tiny piece of that path. And then let's say you have a force here. Let's say the force is a constant force pointing this way. The idea is if the force was always directed straight up, actually, let's do a simpler one. Let's do straight down. Okay, apologies for that. We know, imagine this is a drone and it's flying around in this curved path and gravity is acting straight down on it. Okay, you have no problems believing that gravity is going to act straight down on the drone regardless of its path. So that's the force vector. The idea here is the force dot the displacement, and then you integrate over every possible displacement will give you the work done by this. Work in physics relates to change in kinetic energy, another topic we haven't talked about. So I'll bring that up in just a second. But I do want to point out here, look at this angle right here. And if I could make this arrow a little bit bigger so you could see it. Let's say this is ds and this is a force, gravity. Is this contribution to the integral positive or negative, or is it impossible to determine? I'll give you a hint. There's a dot product in the definition. It's F dot displacement. Do you remember anything about the dot product? Okay. I'm just going to move this up here so I can draw something. What's this angle look like to you? Just eyeball it. It's okay to be just approximate. What do you think? Like maybe 120 or something, maybe? Maybe let's say 130. Let's say that angle is about 130 degrees. That seems reasonable. How do you do the dot product? Isn't that F let me just say theta for right now. Whoops. Isn't that essentially the dot product? It's the two vectors' magnitudes. Let me color this in green so it matches. The force vector magnitude, the displacement, even though it's tiny, it's still got a magnitude, times cosine of the angle in between. When you put in 130 degrees, is cosine positive or negative?
Positive?
Negative. Just punch it in on your calculator. I just realized an awesome April Fool's prank you guys should try and figure out. When I go to this mode, I can't see any of your faces. You could all just leave the Zoom meeting and I'll just be talking to myself. It'll be like what happens with me and my kids all the time. They just leave the room. I don't realize. Anyways, never mind. Yeah, cosine of 130 is a negative number. All right. So, okay. Don't overthink this. This is a very complicated looking definition. What we need to know right now is it relates to the force and then the angle and the distance you travel. That's what you should get out of this. Next, you should also realize that work could be negative. Okay. So work could be a positive or negative quantity. And in general, as objects move around in real life, look at this one right here. If this object is, again, a drone flying around, at this point, the force vector is down, but ds is pointing this way. So notice the angle over here is more like, let's say this is about 75 degrees. I'm just eyeballing it. So notice sometimes when the angle is bigger than 90, you do negative work. When the angle is less than 90 degrees, you do positive work. Okay, I'm going to pause for a second, see if you have any questions about this concept.
So does the negative work mean you're expelling, right?
Let me help you with what it means physically, because right now I just wanted to point out it can be positive or negative.
Okay.
It sounds like you're good with that, right?
Yeah.
Okay, so to understand the physical meaning of this, we need one more step. Okay, now in this case, it turns out I'm going to talk about a thing I'm going to call K. Sometimes you'll see me write it as KE, or sometimes you'll see me write kin erg. So this is kinetic energy. This is a new term. Now, energy is something we haven't really talked about at all yet. However, you can think about energy as something's ability to cause pain. If you have a lot of energy, like you could think about a bullet is traveling very fast, it could kill you. It has a lot of kinetic energy. Even though it's small, it has a lot of kinetic energy. And that gives us some inclination already that kinetic energy must relate to an object's mass and its speed. And in fact, it does in this unusual way. Here, this is mass. Give me a sec. This is mass. And notice there's no vector on here. This is speed. Okay, so, and the equation that helps us relate these two, why am I bringing this up? It turns out that work equals change in kinetic energy. This helps us understand something. If you have positive work, you have a positive change in kinetic energy, you usually increase something's speed. Right? You're not going to change an object's mass usually. We could worry about that if we're doing some complicated, weird scenario later. But yeah, for now, the idea is negative work then means you slow something down usually, or try to slow something down. Esteban, does that help?
Yeah, I'm trying to relate it to chemistry when we talk about doing work or work being done to it.
Yeah, are you talking about PV equals nRT and gas laws and all that?
Mm-hmm.
Yeah, I could tell you a lot more about that right after class, but for right now, I've got a good way of talking about that. Okay. It's just basically for us right now with particles, let's think positive work, speed something up, increase its kinetic energy. Negative work, try to slow it down.
Okay.
All right. And again, I'll talk to you about work done by versus work done on at the end in office hours, because I've got some tricks for that. Okay. So, and we get to that in Physics 162. So now from a practical standpoint, if force is constant, it pops right out of the integral and you get this. Now, I just want to point out, let's see, you could actually do the integral this way. You could split your force, right? You could take the force and split it up into x, y, and z components and do an integral over the x. Oh, whoops, that should be a y, shouldn't it? So correct that in your notes right there. I'd never noticed that before. This should be a y right there. Let me make a note of that. Got it. All right. Or this was the integral I was showing you. So this is a very difficult integral to do in general, whereas this is pretty straightforward. You split the force up into x, y, and z components, and then you just integrate over x for the x component, etc. And this is what I was just alluding to. Work is equal to the change in kinetic energy. If you're wondering where this comes from and how they chose to define it this way, whoops, look down at the bottom of the page while I'm clearing my annotations here. This is the theorem. If you're curious where it comes from, there's the derivation. We're not going to use that derivation. We're going to use the result of that derivation. But this kind of walks you through, why are we getting this 1/2 mv squared? Look right here, right? What I did is I took the force and I changed it to ma. Again, we're assuming constant mass for right now, but this actually works even when mass is not constant. But for right now, we're going to stick with this. All right. And then this is a trick that students might not be used to. I remember the first time I saw this, I felt uncomfortable. But it is legal to rearrange the orders of differentials, because once you cut these things up into tiny little chunks, we assume that it's basically a parameter or a number that you could switch back and forth. And if it's not true, then you just cut it up even smaller until this is legal. So this is a crazy, uncomfortable looking feeling. But by doing this, we get the dx up here, which allows us to write this v, and you're good to go. Now, you could do the same thing, and if the force has a component in the j hat and the k hat, you get something very similar, and you get vx squared, y squared, z squared, etc. All right. In this chapter, we're going to switch between displacement and distance very often. And so the issue here is, as long as an object is moving in one direction, we could use the Harry Styles theorem. And oh my gosh, I can't believe, I just want to puke right now. Whatever. Like, yeah, let's see a worked example. All right. So, let's see. Let's say we have a constant external force. So I'm looking at the next page, page 4, trying to get over this fact that I even know who Harry Styles in One Direction are. It's making me want to kind of feel ill about myself, but what are you going to do? All right, here you go. Work. So here's an example. Let's say the tension is 12 newtons. The angle is 10 degrees. Your distance is 3 meters. We just say, okay, plug in. And this, I want to point out, this is an example for a constant force. So many of our forces in our FBDs are constant, right? For example, if you're on an inclined plane and you're a block going up the inclined plane, the normal force isn't changing. mg isn't changing. Maybe there's a frictional force. That's not changing. There might be a tension on a string at an angle. That's not changing usually. So this constant force trick will help us out a lot. We just plug in the magnitude, the displacement magnitude, which is the distance, and then the angle, right? And we get a number. Now, this Newton meters is very similar to the unit of torque, but this is an energy calculation. So you're supposed to know, oh, work and energy are in units of joules, a real gem of a unit. All right. You could do this problem another way. Look at this same example. Whoops, let me clear those annotations. So sorry for this long screen share. I don't normally like to do this long, but it's just nice that it's all worked out here. You could actually split the problem up this way. You could split the force into an x hat and a y hat, or I hat and j hat components. And then what you could do is you could figure out the displacement in I hat and j hat, and then just say, okay, multiply the x displacement with the x component of tension, and you get the same answer. So you've got this example right in front of you, but I just don't know. Are there, let me go back to gallery view. So far, so good on the constant force example. Any questions about that before I go flying past? Sweet.
Go ahead. Calculating is always in a dot product, right?
Yeah, there's a dot product in here, which is why we had to do that chapter 3 stuff in 110 and there, yeah, because we're going to use dot products all the time now.
Okay.
And then in 2 chapters, we're going to use cross products all the time. All right. Some of you might be saying, you know, I already know about potential energy. I don't need this chapter. It turns out you can never really get away from this chapter, because in the real world, some forces you can't write energies for. So if you don't know what I'm talking about, don't worry about it. If you do, then just trust me, I know what I'm talking about. It's important that we actually do this chapter. Let's look at 7.1. All right, why not start easy here? So I'm going to get this one up. Let's try and use this new technique of work to figure out the change in speed and discuss it. So I'm just going to get the problem written up. (7.1). We've got a block. Oh boy, it's one of these ones. A force is applied horizontally. We're going to move some distance here. Let me. Notice, this is subtle, but when you're drawing pictures, you got to be a little bit careful here. I just want to point something out. Notice I went from the front of the block to the front of the block. If the block has negligible size, this is not a big deal. But it's important when you're showing where things go. And if things start moving in circles, technically we should probably go from the center of mass to the new location of the center of mass. But I hope you agree that distance is also exactly the same for this case. So in this particular case, just watch out when you're drawing your pictures. Make sure you show the actual distance the object moves, not this distance right here. That distance is not L, that last one that I drew, the bottom one. Okay, so that is not L. You got to be a little bit careful when you're drawing here. Okay. All right, so here we go. Whoops. Wait, I need speaker view. There we go. Okay. Okay, so we got this picture right here. There's an FBD. Somebody shout out one force on this object.
Normal force.
Normal force, which way is that?
Perpendicular to the slope.
Yep, got it. There's normal force. What else? How about mg? I'll do the easy one. Ha 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 ha. Well, I guess there's this one. What else do we have? Anything else? Is it
Friction.
is there friction? Okay, which way is it moving?
Down the plane.
Is it moving down the plane or up the plane? Oh, friction points down the plane. Okay, so I'll draw that right here. Oh yeah, it's moving up. The block moves up the plane, so friction points down the plane. Yep, I think that's all the forces. Agreed? So, all right, so that's part A, done. We've done part A. Next, it says, determine an expression for the normal force. So we're supposed to solve for n. What coordinate system would you use? Oh, wait a minute. Is this accelerating or not? Do we know if it's accelerating or not? What do you think?
It says the magnitude of acceleration is due to gravity g.
That's the magnitude of acceleration due to gravity. That's just saying g is g. So that's basically telling us we're on Earth. It's not telling us the acceleration of this particular block is g. Do you agree that would only be true if you dropped it?
Mm.
So that's a tricky subtlety. So that's just basically saying g is a constant you could use in this problem. So, all right. So what do you think though? Is it accelerating?
Yes.
We know it's moving, but we don't know if it's accelerating.
I would say exactly that. We know that it's going to move up the plane, but we don't know its initial speed. We don't know its final speed. So the safe thing to do is assume it is accelerating, and then we could figure out that value later. But we certainly do not know that A is 0. There's no indication that this is at constant speed. Do you agree? So the more general problem we could do in this case is assume it is accelerating. And this is one of the subtleties, right? So physicists are notorious for making you use your brain to figure out an assumption. They're like, well, look, I never said it was constant speed. The more general case is to assume it is accelerating. So we're going to do that. Does that make sense? In the end, what if it was slowing down? I should get a negative number for A. So I'm going to assume that it's accelerating in the direction I push it. And then later on, we could find out that something, maybe the friction was overpowering it. Maybe you start out at 10 miles an hour and end up at 8. All right. Okay, so we're looking for N in the next part, right? Which coordinate system would you choose? Would you use the standard XY or the rotated XY? What do you think?
Lined up with the slope?
Yeah, let's try that. So because this looks like it's going to match up pretty well. So which forces do I need to split up?
MG and zombie force?
Yeah, MG and the zombie force. So we're going to get a force here. So if this is theta, what's this angle?
90 minus theta.
Then this
Theta.
one is theta. Yep. So this is theta. And then what's this one in here?
Now it's theta.
Theta, yeah. So every other one is theta. All right. So in this case, go ahead and write down the force equations you think, and then I'll take a sip of water and try to catch up. So write down what you think the force equations are. And again, we want to get the normal force, I think, right? So is that what you got? Normal force up. This side, let me get a pointer. This side right here is adjacent, so that's going to get you mg cosine, and it's down. This is opposite theta, so that's f sine theta, negative, and then equals 0, because this acceleration is parallel to the plane. There's no acceleration perpendicular to the plane. So far, so good? So there's the normal force. That's part B. And it's hard for me to tell if this is sinking in at all. So please just hit unmute or yell at me and say, dude, I don't understand. If you do understand, good. I'm just going to kind of keep rolling along slowly, but stop me at any time. Okay, we're supposed to get the expression for the frictional force. All right. In this case, which frictional condition applies?
Kinetic.
Yep. So finally, we get an easy one. Whoops, I just wrote mu static. Well, that's pretty easy. It's just mu times that. So I'm not even going to write it again. But since we know what n is, now we know what f is. I'm going to read the next part. Part D. So maybe I'll label these just so in case somebody's following along. This was the answer to part A. This was the answer to part B. This was the answer to part C. So now we're up to part D. And let me scoot back a bit and do this. Part D says, determine the work done by the force F. Okay, so finally we get a new piece of information. The work done by force F. This is how I'm going to write it. I'll do a capital W with a subscript F. And then what I almost always do in this type of problem is draw a mini picture, right? Because we know from the definition, it's F dot ds, and then you integrate it. We do not want to do this because this is ugly. It's essentially equal to, because F is a constant, we don't even do this. We skip right to F times distance times, and I'm going to just write this way, F times distance times cosine of the angle. All right. So that is the trick that we're going to use. In this case, I oftentimes draw a picture right below here. You don't have to do this step, but you also don't have to get the answer right. Okay, when the problems get harder, this is when this technique will be useful. In this particular problem, the distance is L. The angle happens to be theta. It's not always theta. Sometimes it will be 90 minus theta or 90 plus theta or 180 minus theta. So we have to be careful here. It's not always theta, but it usually relates to theta or 90 or 0. Okay, or 180. All right. That's it. Cool. And now, what's part, any questions about that? This little sketch just showing these, make sure I could tell something right away. When I see these two forces, or sorry, I should be careful. This is a distance. And so I guess technically this entire arrow would be a displacement. Where's my marker here? I just want to make this look a little bit more like an L. Right? In this case, I could see that the work should be what? Positive or negative? What's your gut tell you?
Positive.
Positive. The angle's less than 90. Let's also look at our picture. If you push on this block and it's moving the way you push it, shouldn't this force tend to speed you up? This seems entirely plausible that the work done by F should be positive because, again, we know the block is moving this way. The force, it's not perfectly pushing that way, but it's pushing almost that way. So we expect the work done by this force should be positive. All this makes me feel good with that. When I plug in F, a positive number, L, a positive number, theta less than 90, I expect a positive work. This makes sense. All right, so I'm starting to run out of board space. So I'm going to, well, I'm just going to erase these ones. We've got those. We're good to go. So what's part E? Determine the work done by gravity. All right, so this one, I'm just going to go to the solution here just so we can walk through this. If you have the solution open, that's fine. So again, there's the question. We're up to work done by gravity. This one gets sneaky. Okay, so there's our FBD. This would be that same picture of showing the work done by gravity. And this gets confusing. Notice here's the displacement. Here's the force. The angle between them is not 90 degrees. It's not theta degrees. It turns out it's 90 plus theta. Now, if you're curious, cosine of 90 plus theta happens to equal negative sine theta. So the answer for this one should be the work done by mg should equal the force, that's mg, times the distance, that's L, and then times the cosine of the angle between. That happens to be 90 plus theta in this case. But nobody would ever write it that way. We would immediately use this trig identity to change this to sine theta. And this shows you why, man, not knowing all the different ways is kind of painful. I'm going to show you another style that makes this a lot more intuitive in just a second. All right, but any questions about the work done by mg? I know this seems a little strange, but when I get to work problems, I think about Miller genuine draft, because a lot of times you get MGD. I don't know what that says about me as a human being, but that's what I think about. How many MGDs you got? And so even though that's silly, if it helps me remember, that's basically checking the units, right? I need a mass, a G, and a distance to get work. I need MGDs. I need those MGDs. All right, whatever. Look at this blue style down here, right? So look at this case. We see, consider the component of mg parallel to displacement. This is another way to do it. Mg sine theta is the force that points downhill. L is pointed this way. So I could actually do it this way. I could say work is equal to force parallel times the distance. Well, the force parallel in this case is negative mg sine theta because mg sine theta is anti-parallel. So that's the force parallel. And D is L in this case, the displacement. So both of those ways show you that the work is negative mgl sine theta. Okay? So that's the work done by mg. I'm going to pause for a second. Any questions about that? I guess you could always go back to this style too. Work is equal to force dot displacement. Right? And that's where this force parallel comes from. The dot product in mathematics picks off the component that is parallel. If you were really frisky, you could say, well, wait, couldn't I just do force times displacement parallel? Absolutely. Either one would work. So there's other ways. Okay. I should stop now and go on to doing the problem. But any questions? Any questions about this? These are all just different ways to do the same thing. All right. So let's go back to the question now. Okay, we've done this. We've done this. Determine the work done by friction. Okay, let's go look at the solution for that one. Oh, that's kind of, all right, let's go to the whiteboard for this one. Sorry about that. Okay, the work done by friction notice why it's nice to have a capital F and a lowercase f, so we could tell the difference between work subscript capital F and work subscript lowercase f. And let's even do this one in green so it matches up there. Work done by friction is equal to the frictional force times the displacement times the cosine of the angle between. What is the angle between in this case? Let's draw the picture so we don't get lost. Friction points down the plane. My displacement is up the plane. Is it theta or 90 minus theta? Whoops. What's the angle between?
Isn't it just 180?
It is 180. I was trying to mess with you. Sometimes people will throw in theta when it shouldn't be theta. In this case, it's just a number. It's 180 degrees. Whoops. Right? So then this one's actually pretty easy. The distance is L. The angle for friction in this case is 180 degrees. It's usually 180 degrees. Usually friction points opposite the way you're moving. Not always. We've discovered that with cars or with boxes on trucks that are sliding forwards. Okay. And here, friction, well, that's just mu times this big ugly formula. Done. So you could take mu times this, shove it in there. What's cosine of 180?
-1.
So this ends up being negative FL. Wait a minute. Does the negative work make sense for friction? Think about it.
It's slowing you down. So
Friction is trying to slow you down. Exactly. And this explains why we don't know which way this thing is accelerating, right? Because look, if you're pushing on it, okay, let's say it starts out at 10 miles an hour and you're pushing it up. Well, this force is obviously going to be doing positive work, trying to speed you up. Friction is going to do negative work, trying to slow you down, and we don't know who wins. There could be more friction than zombie push, right? And so in this case, we do know that this is a positive work term because it's trying to speed you up. We don't know if it succeeds. This is a negative work term because it's trying to slow you down. We don't know if it succeeds, but that makes sense. Questions about that? That's how you check your signs on these. And this picture helps you kind of feel that. You're like, huh, friction's opposing my motion. Probably tries to slow me down. Should be a negative number in the work equation. So I did one last step. Let's check the solution really quick. Oh, there it is, right there. So notice this is the equation. Whoops. It's, okay, so let me be careful here. Give me just a second. Mu times all of that, right? Remember, this is the normal force. In this case, that's the force. Here's the distance, and this is associated with that 180-degree angle. Whoa, look at this one. I just said it's 0. What? Let's go to the work done by the normal force. How did I know the work done by the normal force is 0? Let's draw a picture. Okay. By drawing the picture, you understand it better. It's not required, but if it helps you pass, let's do it. Okay. The normal force is pointing this way, right? Perpendicular. This is L, the distance I travel. That's the sloppy N. I'm going to rewrite it. What's the angle between?
90 degrees.
90. What's cosine of 90?
0.
Yeah, boy. All right. So this drops out and becomes a 0. So in general, forces perpendicular to displacement do no work. Now, this is Zoom. It gives me an excuse to repeat myself because maybe I lagged. I'm going to say that again. Forces perpendicular to displacement do no work. All right. Now, that doesn't mean they don't do things. The normal force clearly keeps this block from falling through the floor. If you didn't have a normal force, it wouldn't move in this way. So clearly it's involved. And the normal force relates to the frictional force. So all of this stuff matters, but we could say from a strict physics definition, the normal force does not speed you up or slow you down. It's perpendicular to your motion. Let me give you another example really quick. Oops. Let's have a ball here. How much work is being done by the tension in the string as this ball orbits?
None.
None. It's perpendicular to the motion at all points in the motion, right? Well, think about it. If I spin this fast enough, do you agree it's basically a constant speed problem? So the tension clearly does something. It keeps the ball moving in a circle, but it's not what's changing the speed. Even if I slow it down, gravity is changing the speed as it goes up and down. Gravity is not always perpendicular to displacement. But if this string's moving here, the string is always perpendicular. So circular motion will be interesting when we analyze that with work. But the short version, I'll say it a third time, forces perpendicular to displacement do no work. They matter, they're important, but they are not involved in a work calculation. And this is one of the reasons this chapter is cool. It gives us a shortcut. Okay. All right. Probably doesn't feel like a shortcut. We're going to take a break as soon as I manage to get through this. Oh, come on. Hold on. Zoom's locking up on me. Okay. There we go. Sorry, it was doing something weird. All right. So we got this. Now, here's the thing. We can actually figure out the speed of the block without figuring out the acceleration. What we do is we say, get the net work on this block. Add those all up, and that relates to the change in kinetic energy. So now we're told the block, assume the block starts from rest. Aha, clearly it did accelerate to the right. So now we know. But if I go into the solutions, this is the answer you get for the velocity. What did I do? I just took, well, let me zoom out just a little bit here. Okay, let me scoot up. I take, oh, whoops, I can go down just a hair. There we go. Oh, sorry. Yeah. All right, there we go. We've got it all. Here's the work done by the force applied by the zombie. Here's the work done by gravity. Here's the work done, oops, by friction. And here's the work done by the normal force. The work net is just add those up. So in equation form, work net in this particular problem happens to be work friction plus work F. I said those backwards. Plus work done by the normal force plus work done by mg. You add those all up, and that gives you the net work. Well, I know that work net is equal to the change in kinetic energy. The change in kinetic energy, by definition, is 1/2 mv final squared minus 1/2 mv initial squared, because the definition of kinetic energy was 1/2 mv squared. So I'm going to pause for a second. I add up all those equations that we had before. That goes into this side. This is a definition called the work energy theorem. That's where this equation comes from, the work energy theorem. I know this particular thing started from rest. This term drops out to 0. Afterwards, notice I'm going to get a 2 over m and a square root. That's where the 2, the m, and the square root, and the rest is just kind of grouping terms. So you could practice your algebra later to see if you can get the answer, part H. I'm going to pause for a second. Any questions on that?
I know this might be getting slightly off topic, but
Go for it.
if we're assuming that it's starting from rest, wouldn't we also need to include mu static?
Yeah. So that's an excellent question. Let me ask you this. Percentage-wise, this thing's going to move all the way across here, right? You're talking about one tiny moment in time right here. Agreed?
Yeah.
And percentage-wise, that would be completely negligible. So we could feel free to ignore that. However, we could even go stronger. If mu static is still applying, is it moving yet?
No.
What's the displacement while the force is static friction?
It's going to be 0.
So what's the work done by static friction?
0 as well.
Yeah.
Right.
And so you could argue it in either of those two ways. I think the second one is probably a little bit stronger. So, yeah. Cool. So could static friction ever do work? What do you think based off that? What do you think? Could static friction ever do work?
I want to say no.
So what do you think I would say?
You're probably going to say yes.
Can you imagine a situation where static friction actually does work?
If you're pushing on it and it still doesn't move?
Let me give you a simple example. This is supposed to be a truck. Okay, so in this case, now let's think about this. Let's say you put a box on the back of this truck and assume this box does not slide. Assume the truck starts at rest. If it's initially at rest, let's take a look at this. In this case, what force keeps the box on the back of the truck as you drive forwards, if you accelerate forwards?
Static friction.
Oh, so wait a minute. You just told me static friction makes this block go forwards. Agreed? Does static friction tend to increase or decrease the speed of this block? Do you agree it does positive work?
Yeah.
Isn't that weird? Now, you don't get something for free here. By Newton's third law, isn't it acting backwards here as well? So it does no net work on the box truck system, but it does do positive work on the box. And so we see it is very crucial to make sure we clearly state all the subtleties of the problem. It's sort of like that word relative velocity, like relative to what? Boy, that sure matters in some problems. And so here, the box does not move relative to the truck, but it does move relative to the earth. Clearly, this box has gained kinetic energy relative to the earth. And we understand this problem as if we're sitting on the earth, we view it as this box is not moving and then it is moving. Clearly, it gained kinetic energy the only force that it could possibly be is that frictional force. This shows you why it gets tricky in this chapter. Is that good?
Yeah, that was perfect.
Very sneaky. Yeah. In general, you're right. In general, for boxes that are sitting at rest on a plane, static friction wouldn't do any work. But we see it a lot doing work a lot of times in these kind of stacked blocks. You could view this as a 2-block problem, right? If I was really creative, I'd just say, imagine truck is a block. And so if you have a 2-block problem, static friction tends to do positive work on one, negative on the other. In fact, I know it's time to take a break, but I just want to point out something that you just asked about, I think, if I'm not mistaken. Ha! There it is. So you asked the question at just the right time. So, whoops, I just screwed up and, well, we basically did that problem right now. So let's go ahead and take a break because it's been an hour and 20 minutes. We got to take a break. So, everybody take a quick break. You could look at 7.2 if you want, and that kind of gives you some, hopefully that makes some sense. Whew. Yeah, I need to get more water. I'm running out. All right, we'll come back here in about 10 minutes here. What time is it now? Let me get out of full screen mode. 1:23. So let's come back at say like 1:32, 1:33, somewhere in there. Any other questions? You could take your break. Anybody else that wants to can ask a question as well. All right, I'm going to get some water and I'll come right back if you need some time to digest. Still have plenty of time, but I'm here if you do have any questions, okay? Still got 8 minutes. Almost ready to go here. About 45 more seconds. All right, probably a good time to get going. So you might be asking yourself right now, why are we doing this? This seems like a lot more work. We need one of those, but yes. So let's talk for a second about why we should care. Because for me, it's a lot easier to study something if there's a reason to care about it. I just want to kind of think about what we've been doing in the class up till now. We've basically been doing two techniques, forces and kinematics. Okay. So now we've added, and you could say, well, what about vectors? I could argue, okay, that's included in both of those. So vector is the mathematics that we use in these. But essentially, we've basically done kinematics, either 1D, 2D, or 3D, and we've done forces and nothing else. So now we have a new technique. This is something completely different in our toolbox. Not walk. That'd be tasty, but we're going to introduce this new tool, work. And you may not have noticed this, but in the previous problem, let's say we wanted to get the speed of the object at the end of the problem. We would have first done forces, done a lot of different calculations, determined the acceleration. Then we could take that acceleration, plug it in here, and do a kinematics problem. So while at first it seems like this was a lot of effort, I picked a pretty complicated problem so we'd have a lot to talk about with a lot of different angles. But in fact, it is slightly faster to calculate speeds this way. And so it is actually a shortcut in certain cases. So you can think of this class in general as building yourself a physics toolbox. There are different tools we can grab to learn things about the natural world. We could get something out of our kinematics toolbox to analyze motion, or forces. We could analyze it in a different way. Now there's this new topic, work and energy. And in the next chapter, we're going to modify this technique to make it easier to use. So we have to first understand the basics, and then in chapter 8, it's basically all shortcuts and tricks to make this technique even easier. And what we will find is these two types of equations are great, like forces are great for analyzing accelerations. If we want to know about an acceleration, we will learn soon enough that work and energy are great for analyzing speeds. So if we want to learn about a speed in a problem, usually I grab for a work energy tool rather than a force tool and kinematics. And that is the big picture why we should care about it. All right. Any questions about that? All right. And you can interrupt at any time if I didn't give you enough time. The rest of the problems on this page, we discussed this already. You could do that again tonight and see if you remember it. 7.3 and 7.4, those are very similar, and it just gives you a chance to kind of practice these things. And notice this one, it's not even having you do all this. It's just trying to make sure you check normal forces and which ones are work, which ones do work and which ones do zero work. All right. So all kinds of different stuff. Ooh, this has got a zombie with a nanobot releasing a chemical. Man, that sounds like a good problem. All right. So let's go to this one. 7.5 on page 6. Take a second to read this one. A car drives on a banked curve. Oh, the fun never ends. It's in a circular path of radius r, and it's driving with speed v. Okay. The curve is angled. Okay, so it's a standard bank curve problem. The car is driving at the maximum speed possible without sliding to the outside of the track. The coefficients of friction between the tire are, okay, great. Be sure to determine, okay, so let's just think about this. What is the work done by the normal force if you had to guess? Go ahead and unmute and take a guess. Or how would we proceed? What might you do? Oh.
Would normal force be 0?
Normal force is not 0. I think you meant the work done by the normal force. Agreed?
Right.
Sorry, yeah, I'm just trying to, so I'm just trying to use the right words. So you're right. The work done by the normal force is 0. How do you know it's 0?
Anything perpendicular to the displacement is 0.
Exactly. So how do you think we would proceed if we wanted to figure out the work done by gravity?
Probably make an FBD so that way you have a visual.
That's what, okay, so here's the normal force. Here's mg. There's friction. Which way is friction pointing on this case?
Would that be down?
Down the plane, yep. Let me label these so we could follow. All right. Okay. Now, in this case, we usually go right to work done by mg, right? And that's equal to the force times the distance, mgds, times cosine of the angle between. What's the angle between? Remember I mentioned it's sometimes useful to draw a little picture? Here's mg. At the instant shown, what direction is displacement?
Shouldn't we try to get like a top view of the?
Okay, you want a top view? I'll draw a top view. Here's the top view. Here's the car. Which way is, let's say it's going this way, right? Which way is mg then?
We can't see MG from that view.
So it would be, say the words into or out of. That will help.
Into the page.
So what's the angle between?
90 degrees.
90. What's the work done by gravity in this problem?
0.
Here's friction. What's the angle between friction?
Oh man, 90.
So they all do no work. The answer, it was a trick question. I love it. You guys did perfectly. All right, so nice job. So here's the answer if I could clear out my junk. All the forces are perpendicular. This is not a problem. Remember, the wording of the problem said the car travels at some speed. That implies the speed is constant. That means kinetic energy is not changing or work is 0, and there's no work at all in that problem. So notice this is not a good tool for objects traveling at constant speed because there's nothing to calculate. So this tool has its limitations. Here's another example. Gravity pulls the Earth towards the center of the orbit of its orbit, right? The work done by gravity is 0. Lucky for us, the Earth is not changing its speed. All right, so we're good to go there. So cool. If we're in a circular orbit, our speed remains constant, just like the ball on a string. So now be careful. Velocity changes, speed does not. And so there are limitations to this technique. Basically, we can't use a work energy for every problem. All right, nice job. That was a trick question. It's kind of uncomfortable feeling when you say everything is 0 in a problem, but that's okay. So that was just, you're supposed to look at that and just say the answer is 0 for all three. All right, so it's counterintuitive. All right, we've discussed constant forces. So now what if we do non-constant forces? We're going to basically restrict ourselves to one-dimensional non-constant forces. Because if I have to do 3D vector calculus, not everybody has had 3D vector calculus, okay? Not everybody's had Math 183 already. So here is the integral. This is the original definition of work. And this gives us the work done by a force that's changing. And springs are a particularly useful thing. So if we want to understand, we've ignored springs right now because you probably know this from experience. If you stretch a spring, the more you stretch it, the larger the force is. Okay. If you don't believe me, get a rubber band, pull it back 1 millimeter and hit your face with it. Then pull it back 600 millimeters and hit your face with it. It hurts a lot more the more you stretch it because it's got more stored energy. Anyways, so clearly the force required to stretch it is also larger. So now I want you to read this very carefully with me, all right? Here's our first very, very useful non-constant force. The force due to a spring. There's a negative sign. What does that mean? If I stretch it to the right like this, the force is to the left. If you compress it, if I had squished it, then the force would be to the right. That's what this minus sign right here means. Okay? That makes sense. K is a constant. It's basically relating to the stiffness of the spring. If you have a very strong spring, a very stiff spring, you would have a large value of K. If you have a weak spring, you'd have a small value of K. So that's just a constant, nothing special. Delta X is the displacement of the spring from the unstretched position. I cannot say that in fewer words without making a mistake. However, usually in any spring problem, rather than choosing X wherever you like, we choose X to be the unstretched position. If you set X to 0, right, delta X, sorry, X initial to 0, would be something like X final minus X unstretched. I'm going to say X un, okay? So in this case, you could choose your coordinate system wherever you want. So why not set our coordinate system at the center of this block when the spring is unstretched? Okay, so that sends this to 0. That means I don't need this subscript anymore. And that means delta X just becomes X. So take a second. I'm going to pause. Is everybody okay with what I did right there? Notice this is a vector. It's a vector. Underline that word vector. And this is position X. Could be positive or negative. You could stretch or compress the spring. Now, a lot of times in physics, we do free body diagrams. And in those free body diagrams, we draw force magnitudes. And this drives students crazy at first. Here, this is a magnitude. It's positive. X is a distance. And so notice this quantity right here, the force done by the spring, is going to be a positive quantity. So there are multiple, we see here 3 different ways the spring force is written. And if you are reading a textbook and you're a student and you're learning for the first time, you have to look for these carefully. Did they use the delta? Did they drop the delta but keep the vector? Or did they drop the delta and the vector and are just talking? So this gets complicated. It's just like G versus AY. We have to be very careful. Are we talking about acceleration, which needs the minus sign explicit? Or are we talking about the magnitude, which doesn't? Woof. Enough said. All right. Any questions before we do the problem? So this again is on page 6. We're looking at 7.6. I'm going to write it up on the board here. Okay. It's going to get cooler and cooler every week from now on. Okay, harder, but cooler. All right. All right. So in this case, we're supposed to first check the units. Well, the units of F equal the units of K times the units of X. So notice we're going to get the units of K equal, that's a loud car. Don't overthink it. Notice you keep the brackets on until you get the units. So the units of spring constant are newtons per meter. If you have a bigger K, you get more newtons per meter. Okay, you get more force per amount of stretch or compression. Okay, so that's part A, nothing to see there. Let's get back to it here. Let's see, what was part B? Part B said, okay, determine the work done as it goes from 0 to stretched. Okay, so in part B, they want the work done as we go from 0 centimeters to 6.0 centimeters from the force due to the spring dot dx in the I hat. All right. Let me just get this a little bit higher there. This is what we were asked to do. This is the work done by the spring. Any questions about what I did there? This is just the definition of work is always integral of force times displacement. Now, before, maybe you're wondering, why didn't I write ds? I could. Well, ds in this case is just dx in the I hat. And I think I may have miswritten right a second ago. I shouldn't have had both the vector and the I hat. If I did do that, I don't know. I erased it, so I'm in the clear anyways. But you could go back and watch the live stream and say, damn, that Jorstad, he's so terrible. All right. But in this case, I'm moving in the x direction in the positive I hat. That's where this is coming from. So let's plug this in. Notice I'm being very careful with the vectors during this first problem. 0 to 6 centimeters. The force is negative k x vector dot dx in the I hat. Well, by definition, isn't this x vector also x in the I hat? So in this particular problem, everything's going to the right. So that's how I got these I hats involved instead of a ds. And generally, this is what we do. Now look at this. What's I hat dot I hat?
Isn't it a 1?
It is. Chewbacca hat dot Chewbacca hat is 1. Any unit vector dotted with itself. Taco hat dot taco hat. Okay. In Germany, Pizza Hut means pizza hat. Pizza hat dot pizza hat. Anyways, all right. Okay, so let's just take this and set this equal to 1. So that gets rid of that, and I can rewrite this as just dx now. So when I integrate this, I get negative k x squared over 2, I believe. Evaluated at 0 and 6. And I believe, weren't we told in this problem, what is the value of k? Did it say? "40 newtons per meter." It was in part A. All right. So for here, we should just plug in the numbers, right? And you stick in 40 and 6 and we're done? Feeling good on that?
Centimeters to meters.
Ah, that Jorstad, an evil Jorstad, has made us think about a unit conversion at the most inopportune time. So we'd better get our units right. This is the step they don't teach you in calculus class, that units actually matter, right? So, which is fine. That's what we're here for. They're supposed to be teaching you all the tricks, and then we use the tricks to do actually useful work. So, all right. Literally, we're doing work. So here, in this case, I have a minus sign. Are you okay that I could actually flip the limits? With a minus sign, you can flip the limits and get rid of the minus sign. And then at this point, the rest is just math. So let's go to the answer. So notice a couple of things here. I got 72 millijoules. So that's the cleaner way to write it than this one. Notice this had 2 sig figs, so my final answer only had 2 sig figs. The work is negative, though. So I'm going to write that here. Negative 72 millijoules. Let me emphasize that that's a negative. Just a second. What do you think? Is that reasonable? When you stretch this thing, displacement was to the right. What direction is the force from the spring as it stretched to the right? This way, right? It is opposing the motion. So it makes sense that it's a negative value for work. So far, so good? Obviously, if you let go of it, the spring would cause the block to go this way. The force is pulling this way. The spring would do positive work if you let go of it and let it fly back to here. So it's right. There's nothing weird here. Obviously, some zombie had to do work the other direction. So the zombie does work pulling it to, I should be careful. I should have used a different color there. Some zombie is pulling this over this way, and the zombie is using some other force, let's say F. So the zombie does positive work. The spring does negative work as you stretch it. Okay. Now, look at this next question. We're going to stretch it from 6 to 12. Hopefully you're not looking at the answers right now, but if you are, you already know the answer. Do you think the work is going to double? Do you think it's going to quadruple? What do you think? Instead of going from 0 to 6, we're going to go from 6 to 12. What's your gut tell you? Is the work going to double, triple, quadruple? What do you think? Is it going to be the same? You're stretching it the same distance. Let's take a look. I have no idea if this is working for you. Oops, wrong button. All you have to do is the exact same calculation and put in different values. And when you do that, it's not double. It's not quadruple. In fact, it happens to be triple. And this is where people get a little bit confused. You're like, wait, there's an x squared in this equation. Okay, sure. If you stretch it twice as far, shouldn't you get twice? No, it depends on the initial position and the final position. So in general, the most general way of describing this is if you start at the same initial position of 0 and stretch it twice as far, you should get 4 times the work. But in fact, if you start at different initial and finals, there's no reason to think there's some obvious correlation here. So watch out for that. All right. Whoops. Let me see here. Now, I mentioned this. It turns out a lot of students, when you see this equation, right, the work is going to be this thing squared minus that thing squared. You can't just take the difference and square it. So that's just a warning, a math note. A lot of people wish you could do this. It turns out you have to do this ugly process. Nothing fancy there. All right. And finally, look at this one. Let's say we take the mass, you stretch it to 12 centimeters in the I-hat, positive 12, so it's over here. And then you let go of it, it's going to go over to here. So let's say this is plus 12, and this is minus 12. You probably can guess, and we'll just say centimeters here. If you release it from this point at rest, its initial velocity is 0. Its initial speed is also 0. When it gets over here to 12, what is its speed going to be? Also 0. It's sort of like the pendulum we saw in the lab, right? When you swing a pendulum back and forth, it stops for a split second at the endpoints. From this information, tell me right now, what is the work done by that spring as you go from positive 12 to negative 12? Take a guess.
0.
0.
0. What's the change in kinetic energy? What's its initial kinetic energy? I should remind you, you might not remember these. Remember, the kinetic energy formula is 1/2 mv squared, right? And the change in kinetic energy would equal 1/2 mv squared final minus 1/2 mv squared initial. So in this case, what's the change in kinetic energy as we go from the initial position of positive 12 to the final position of negative 12?
0.
0. What gives? Doesn't the spring do work to speed you up? Shouldn't there be a positive number?
What speeds you up, then it slows you down.
Exactly. So the trick is the spring does positive work right here. And then the spring reverses direction and it does the same amount of negative work. So again, this is like one of those problems with the banked curve where sometimes the net work doesn't really help you out. Okay, so that's kind of cool. So that's springs. Now, watch out. There's two different types of springs. There's horizontal springs and vertical springs, or springs that have some vertical component. Like you could imagine a car on a track like this, and there's an angle. Why am I mentioning this? For horizontal springs, the unstretched position is also equilibrium. You have a normal force, an mg, and there's no spring force. However, for vertical problems, right, you know you need to have a spring force up the hill to counteract one of the components of gravity. And so this gets very tricky if the spring has some vertical component. So this would be F of the spring over here, and this would be mg. What I'm saying here is for horizontal springs, we can use the words equilibrium and unstretched interchangeably for horizontal only. For vertical, you cannot do that. The spring force is not distance from equilibrium. It is distance from unstretched position. Now, I could tell you that till I'm blue in the face. You won't really realize it until you do a vertical spring problem in the next chapter and get screwed over. So let's save that for then. That's springs. We talked about the spring force, how to get the work done by the spring, and that's great. We still have 15 minutes. I'm going to pause for a second. 80 questions about springs while we got them up there. Let me give you an example of a spring that you might not expect. This is kind of a bad spring. It's very low K. But if I wiggle this just a tiny amount, I don't know if you can see that wiggle just a tiny bit. Or how about, let's see, let's find another object. This is a weird spring. But I'm always shining in my face, right? If you hit this hard enough, anything will wiggle a little bit. And you could view this wiggling motion as being caused by a spring. And so even though this is not exactly looking like a normal spring, the idea here is a large number of problems can be modeled with math and say, well, look, if I hit this thing, it's going to wiggle a little bit. Let's give this thing an effective spring constant and do math with an object as it wiggles back and forth because I just hit it. Let's treat it like a spring, or like flicking a car antenna and it wiggles back and forth, right? You could view that as having some kind of spring constant. Leaf springs on a truck or something, right? They're just pieces of metal laid there. And so there's many different types of springs. There's torsion springs. If you look at your garage door opener, if you have a garage door opener or a garage, right, you could see this got this long spin. And so that one it's all of these different types of springs in the real world are complicated. They all have their own little issues, but they all have something in common where there's some kind of displacement. Like a torsional spring, there's an angular displacement. We could discuss that after chapter 10. But so springs appear a lot in nature. And it's a very good first plan of attack for anything that's wiggling, to treat it like a spring, even if it's not really a spring. All right, whatever. Let's move on. Now, to give you some practice with this, here is a problem where I say, suppose we're going to model the net force on a oh, whoops, I said ball here and bullet here or whatever. But yeah, let's say we want to say the force on a bullet in the barrel of a gun is this. Now, you might be saying, whoa, what is this? This looks like a spring. Yeah, but it's a modified spring. So the idea here was supposed to say, look, during the explosion, there's going to be some kind of force pushing it to the right. And after the explosion, there's going to be an expansion of the air column behind the bullet in the tube, and that's going to decrease the pressure inside. And so that would cause a retarding force, or maybe there's air resistance, or all kinds of things. This model doesn't have to be a good model. And in fact, it's terrible, but it's at least doable for a student at your level. And so that's why I chose it. So in any event, you could take this force and you could do a similar calculation to up here, and you could figure out all kinds of stuff. So I'm going to let you work on that one at home. And then let's see another one. Here's a variation on this one. Suppose you have an electron trapped in a 1D. What? This has to do with electronics? Imagine if you wanted to calculate some information about electrons traveling in a quantum well. This is a very goofy way to do it, but it's foreshadowing physics 163. All right. So this, again, is purely fictional, but calculations relating to this type of thing will show up later. And that's why I bring this up. So again, I'm making up a random problem here to give you some practice. So you can try this, the same derivation that we did again. And if you're curious, I used to work on quantum dots, and that relates to some of this that I'm talking about here. And evidently solar cells are they're trying to come to market this year with some, they're trying to mass produce quantum dot solar cells. Great. All right. More power, as Christopher Walken says in an old James Bond movie from the 80s. I need more power. Power, this is the last thing we're going to talk about today, and this is the last thing. We'll probably start up here next time, but let's just kind of get it all done in one shot. Power is energy over time, rate of change, time rate of change of energy. If you think of change in energy as work, a lot of times you'll hear people say power is work over time. So like if you're talking about how much horsepower your engine has, your lawnmower has, or whatever, that's talking about how much it can change something's energy, how much work it can do in a given amount of time. Okay. So in our units, power will be, the units of energy are joules, and the units of time are seconds. Does anybody know another unit for power? Maybe you've seen it on a light bulb.
Kilowatt hour.
What? What? That's the joke. It works a lot better when it's not Zoom. I'm supposed to be sticking my, you see, hold on. Let's get the joke right. What? What is, so bad. Let's stop that. Hey, I got to do something. I'm talking to a bunch of screens, right? I'm making myself laugh. So, all right. So in this case, just know that the units are joules per second or watts. Now, this is
So, Mr.
go ahead.
Dorset?
Yeah, go ahead.
So what is a kilowatt hour then?
That's a unit. Okay, you just told me the answer right there. So you said kilowatt times an hour, right? Kilowatt hour. So this is what the power company sells you. Are they selling you power? No, that's a bad W. This is supposed to be a capital W. So a watt, that would be kilojoules per second. What's another way to write an hour that we could use?
3,600 seconds.
So what are they selling you?
Just joules.
Yeah, it's about 3.6 megajoules. Do you agree? Because
Yeah.
there's 1, 2, 3, 4, 5, 6 from the kilo. So that's where I get 1, 2, 3, 4, 5, 6. So they're selling you, what is joules a unit of?
It was newtons over meters.
A newtons times meters. So watch out for this. So a newton meter is a joule, and that's a unit of energy. And then a newton per meter was the spring constant. Remember that?
Oh, okay.
So that's the units of K. So we've talked about a lot. So you can see that this chapter has got some fairly simple math, but there's many things that look almost the same. You've got to be very careful. All right. So the power company is selling you energy in units of kilowatt hours. Okay. All right.
So
all right.
why not just call it? Why not just say they're selling you joules? Why specifically?
I know it sounds so much cooler, doesn't it? Well, think about this. Why do we rank food in calories? Why not in joules? In Europe, they do sell food in joules. Right. So like a candy bar, they tell you how many joules you have. So it's, well, let me, I know why. Okay. So from some standpoint, if physicists ruled the world, the units of everything would make a lot more sense. But would you want people like me running the world? No. Right. That's why we use these other weird terms, because people that are better with human beings understand things. And so I guess maybe it helps other people to understand what is a kilowatt hour. Your light bulb is 100 watts or 10 watts. If you leave on a 100-watt light bulb for 10 hours, that's right. Yeah. So I guess we'd have to think about that. It's, oh gosh, that is 10 times 10. So that would be joules. That'd be 1,000 joules. And so I don't know, maybe it's goofy to me, but that's all I can say about it. Is it's better than having physicists run the world, right? Is that good? Esteban?
Yeah. No, every time I've asked that question, I always feel like I just get more lost, because I've asked that question before in other classes, because it's just so confusing, because why it's already a measurement over time, and then they're multiplying it by an hour, and it's like,
well, look at batteries. How are batteries rated? Milliamp hours usually, or amp hours. If you go to buy them, well, what's an amp? It's a coulomb per second. So batteries actually store a finite amount of charge. But the thing is people don't understand it. That one makes a lot more sense, because usually your devices have a rating in milliamps. And so you say, if I want to operate this for a certain amount of time, and I know this, right? So that's the use of it. If you're saying, I know how long I want to operate something that uses this much watts, it's really easy to get the cost. And so that is the real reason you're doing that. It's because it makes it easier to do cost calculations, which that's what people care about a lot more than physics. Is
That makes sense. That
yeah.
makes sense. Yeah.
So it's to optimize the speed at which you can calculate costs. All right. Yeah. So now in this case, we're going to pick up here next time, but there's some good problems here. Let's see. Is there anything else I wanted to say about that? That's it. That's pretty much this chapter. So we'll pick up here next time. So we do have a little bit more. A couple of things I'll end with just before I stop the live stream. I just want to point out some things you got to look out for. Maybe do even a quick summary here. So here's the summary. You could just tune out and you could watch it later if you want. We learned that kinetic energy is 1/2 mv squared. We know that delta K is 1/2 mass v final squared minus 1/2 m v initial squared. And watch out. The most common thing people do with this when they're screwing it up is you cannot do the following. You can't just say this is 1/2 mass v final minus v initial squared. This actually works if v initial is 0 because it drops out, but in general, you can't do that shortcut. So that's one thing. We see that the units of work, they're a real gem of a unit, joules. We saw the units of K are newtons per meter. And so again, this is work. And this is spring constant. So we saw that. Let's see, what else did we talk about today? We talked about there's different ways to calculate work. In general is the integral of minus f, whoops, sorry, not minus. It's the integral of f sub x dx. This is the practical way we're going to end up solving that for non-constant force. And that we saw work is equal to f d cosine of some angle for constant force. These are some of the things that we learned today. I guess another big one is, let me just scroll back a bit longer. Kind of a big takeaway, right? Remember that if work is greater than 0, it tends or tries, it may not succeed, but it tends or tries to speed up something. I'm just going to say OBJ for object. Okay. If the work is less than 0, it tends or tries to slow down object. And work is equal to 0 if force perpendicular to displacement. And I'm going to put that P there and underline that. Displacement. Sorry, there's some glare there. Anything else that jumps out at you, because it's time to end class, but these were some of the things that we talked about today. We will pick up with power next time. So if you want, you could read ahead in that, but I think you've got plenty of work to do with taking a couple of practice tests and doing some chapter 6. We'll see you in lab tomorrow, all right? And we've got office hours right now if you want to keep going.